Welcome to the 1988 Nobel Prize in Physics, which was awarded jointly to Leon Lederman, Melvin Schwartz, and Jack Steinberger. And what they won is for something that's going to sound like a lot of inside physics, sort of inside baseball sort of stuff. But really, what they won was for the neutrino beam method and demonstration of the doublet structure of the lepton through the discovery of the muon neutrino. I know all those words are words, but they just don't make any sense, right? So let's kind of dig into it a little bit. I'm not going to get too deep on this one, but the work was actually done in the 1960s. And the reason it was important was it led to other discoveries and it opened up new research areas for what we believe are the most innermost structures and dynamics of matter. So as you start ripping apart things like, electrons and protons and atoms and pulling them into pieces, you start finding all this other stuff. And now we're saying, people are saying, oh, look, we found it all. That's all the smallest it gets. We found the smallest thing ever. But remember, this work was done less than 100 years after we proved the neutron was real. And actually less than 120 years after the work actually not even 120 years, about 100 years since the theoretical work that there might be a neutron was ever done. So it's, less than 100 years separated from that. And we're not 100 years away from this yet. So have we found the deepest, smallest particle? Maybe, maybe not. I don't know. But it's people who tell you we have. I will remind you that it ain't been that long since we've known about the neutron, or proved the electron was real, or even proved the atom was real for that matter. People thought the atom was real, but did you actually prove it was the other question. So but anyway, all this particle physics stuff, and there's been a lot of Nobel Prizes in particle physics, sound like a lot of, hey, physicists care, but nobody else, right? And that's kind of to some level true. But the technology that has come out of it have caused advances in other fields. They've caused advances in medical fields, they've caused advances in engineering and other areas that you just don't see in the sciences. Now, why is all that important? Why do we care? Well, the reason I think you care about doing science sort of sometimes for the sake of science is you don't know what's going to come out. It could be something highly useful. It could be not something highly useful. But you also want to understand the world around us better. And the more we understand, the more we can engineer better products, the more we can build things like quantum computers and other stuff that wouldn't come out if we hadn't done years of basic science. Now, do we know we've gotten down as small as it's going to be? No, we don't know that. Is this work ever going to be surpassed? Or we're going to come up and say, oh, look, we found something smaller. Is the God particle as small as it gets? I don't know. Only time will tell. Now, the thing that I find interesting about this work was done in the 60s, but not awarded till 88. And what we're going to find in Nobel Prizes from this point forward is the prizes up until this point were people who just didn't know what was going to happen. We weren't quite sure where we were going. It was just sort of, hey, I think maybe this will be interesting. Let's give it a try. Well, what you're going to see in the more modern prizes is less and less risky work being done. And that work and that happens because the way funding has been allocated is you're almost not allowed to have a project not go exactly as you say it would. And sometimes you want to do discovery for the sake of discovery. The trouble is it's expensive. You can't just do it as a hobby. It becomes something that as you get down to these really small particles and you get into these other fields of physics, it's very expensive to do this kind of stuff. It exists at universities. Those universities require funding, but if you're a professor who is not allowed to do anything risky, that becomes a problem. And I'm not talking about this just to say, oh, look, I've studied the Nobel Prize. I've talked to current scientists in the university field, and I left the university personally because it just was getting weird with the fact that you had to almost prove something was going to work before people would fund you to do the work, which was weird. So you had to almost have the work finished before they could fund you to do that last sort of 5%. And I didn't want to do 5% iterative increases. So in industry, you actually get to take more risks than you do in the science area, in the standard science labs. So, the best minds are leaving. And I think not that I'm trying to include myself in the best minds, but I'm just saying the best minds are leaving and going elsewhere because you're allowed to do riskier stuff and certainly it pays better. So I think we need to sort of get a handle on this and say, hey, look, we're going to keep talking about the other Nobel Prizes, but what you'll see is less and less risk and more routine stuff pops out, that nothing of which is really shocking. But it's still kind of neat. But also the engineering in it becomes much more important. So it's more like you have to kind of know what's going to happen. And I think one thing we should do in the United States and globally is fund science that's just sort of kind of for the sake of science. Maybe not with the whole budget. And I'm not saying anything as big and expensive as CERN, but there need to be projects out there that are high risk, high reward. Like, hey, we don't know what's going to happen, but let's give it a try safely, right? And let's do it in some fashion that's reasonably well funded. And I think the way we look at those things does have to shift. And I think you have to get away from sort of the bigger places that are like, hey, we've always done it this way. That's how we're going to keep doing it. You know, you kind of have to go to those smaller institutions and smaller locations that might have a genuinely sort of original idea and go a different direction, not just your Harvard, Yale's, Caltech's, MIT's. And I say that having friends at all those places. So sorry, guys, but we do have to get away from just you guys being the ones that can do everything because you're not taking risks like you used to. We need more risk in the science area and we need more reward in the science area. Otherwise, we're just going to keep getting routine stuff. But this prize was kind of neat because it was something that did kind of help solidify the standard model of physics. And, building a neutrino beam in the 60s was truly original. Big picture of it, it's huge, CERN level kind of stuff. But I really think this prize and all those forward from here, you're going to see much less originality in them, much less sort of creativity in them. And that's what we need to start to foster into our scientific worlds again. And we're going to be talking a lot about that in the new year. So it's sort of tail end of the year right now. We just passed Christmas and next year we're going to start talking a lot more about how we can inject creativity back in the science field and maybe go take those extra steps that we haven't taken recently. So, haven't done one of these videos in a while. Stay tuned, everybody. A lot more of these to come. We're going to finish up through the most recent ones. And then we're going to also dive in the new year. And I've got a bunch of videos pre-recorded into more modern areas of cutting edge research and some areas I'm getting back involved in trying to help foster a way to kind of kick that stuff off into a more aggressive state. So I hope everybody's enjoying these videos. I hope you had a great holiday season and we'll see you soon.